So welcome to the third day of the 13th meeting of studies on the origins of contemporary philosophy. Today, Professor Lydia Patton, who is professor at Virginia Tech, will give a talk to us. And after it, she will debate it, discuss it with Lucas Baccarat, who is a PhD student at the University of Vienna. So without further ado, Professor Patton, the floor is yours.
Excellent, thank you. And I should share the slides, I think, but before that, there we are, perfect. Yes, so thank you very much to Bruno Poli and Mario Gonzalez Porta and everyone at the university for the invitation, and I'm glad to see everyone here. And I'm glad to be presenting on this topic because I've been working on Helmholtz for a while, and yet I find there are a number of elements of his epistemology that are interesting and rather elusive because they occurred in the 19th century context. And so it's kind of difficult to get a handle on them without thinking of them in terms of categories that we're projecting backwards. So I'll say more about that in a moment. But so the talk is about unification before Einstein in Helmholtz's epistemology of science. And so just to start, of course, Helmholtz lived from 1821 to 1894. And he, so let me go back a bit. Sorry, somehow, there we are. Sorry about that. Somehow I managed to skip ahead about 8 slides at one time. Helmholtz lived from 1821 to 1894, and he was responsible for a number of incredible scientific advances in the 19th century. I'm just saying this as a matter of preparation before we get into the talk itself. And one of the most interesting things about Helmholtz was the synthetic nature of his accomplishments. So he, in fact, had accomplishments over a really staggering number of scientific disciplines: optics, ophthalmology, physiology, physics, mathematics, and even chemistry. And so one of the things that I think is most important about Helmholtz in understanding what he wants to say is to talk about how he was able to unify so many results under what he saw as a single set of principles or concepts that he was able to use for explanatory purposes. And so one of the things that I want to talk about in this talk is how Helmholtz's scientific work employed a notion of systematic unification and a notion of explanatory unification, which I'll distinguish. So Helmholtz's unification of science was part of what's often considered to be a broader unification of science in the 19th century. So before getting started, and again, this is all just sort of preparatory, I wanted to note that there are various different ways that we can think about unification in science. So it's often extremely common for people to talk about the unification of science over the late 19th and early 20th century. And of course, relativity theory is considered to be a kind of paradigm case of this. But in particular, there are a set of physical phenomena that are usually considered to be a particular site of unification at the time. So the study of light, electromagnetism, fluids, and sound were all put on a physical basis that in many cases was considered to be unified in various ways. But the first question to ask, if we make these kind of claims about unification, is what exactly do we mean by that? So one common way of talking about unification is to talk about law-based unity. So we talk about the phenomena falling under the same laws, they behave in the same way. This is often considered to be one kind of unification ascribed to the logical empiricists, although as many people here know, it's much more complicated than that. Another type of unity that's appealed to is essential or substantive unity, where one phenomenon is actually considered to be a subtype of another, and they're considered to be the same kind of thing. There's an explanation proposed that talks about one thing being the same as something else. So the statement that light is an electromagnetic wave, for instance, took a long time to establish, and it took a great deal of theorizing to establish over time in Maxwell's theory and others. Now, a third kind of unity that I think is often, like the first two kinds of unity, law-based unity, where we just talk about things falling under the same laws and being explained in the same way, that's quite familiar. Essential unity is familiar, where we talk about, well, we discover that light just is a kind of electromagnetic radiation, and that allows us to unify the theory of light and the theory of electromagnetism, right? Those two types of unity are very well discussed. What I want to focus on in this paper is the distinction between various kinds of explanatory unity, where we talk about explaining the phenomena either in some kind of ontological way as being the same, or in terms of laws of nature or fundamental scientific laws as being explained in the same way. And I'll try to make this more precise in the talk. But I want to distinguish between these and a third kind that's not as often discussed, although it is, namely what I'm calling systematic unity. And this is a more kind of empirical, hands-on type of discussion or exploration, where learning about one phenomenon in practice, in experiment or empirical science, allows us to learn about another by building a system that allows us to show that there are measurable relationships between them. So in particular, I think that the scientific method of the 19th and early 20th century was in the empirical case very focused on proving this kind of systematic unity first, before arguing that there's a kind of law-based or essential unity between the phenomena that are discussed. And so one thing that happens is that systematic unity is analyzed as a way of building a kind of experimental or empirical framework in order to probe measurable relationships between the phenomena that can be investigated experimentally. And so one of the things that I want to discuss here is the role of systematic unity in Helmholtz's theory of fluids. So in order to talk about this, and this is following the order of exposition in the paper, I want to discuss Helmholtz's work in fluid dynamics and how it provides an example of this distinction between systematic and other types of unification that I'm pointing to. So just as a remark, 2021 was the bicentenary of Helmholtz's birth on August the 31st in 1821. So there were quite a few conferences and so forth last year celebrating Helmholtz, his centenary. Again, he's one of the most prolific scientists in history, and of course, even Einstein argued that his contributions were original and free-thinking. This is again a kind of general comment about Helmholtz, but it's worth making. He arrived on the scene in 1821, but of course he really started doing work in science in the late 1830s, 1840s. And this was a particularly exciting time for science, partly because there was really a move from some of the work that had been done in analysis and mathematics in the 18th and 19th centuries to a new set of experimental programs that were getting going in the 19th century in Germany and in the United Kingdom and in France. And there was new fundamental research being done in acoustics, optics, fluids, and electrodynamics. But Helmholtz really thought, and we can discuss this more, but I think that this is really important to him. Not only was he very much engaged in the experimental tradition, but he also admired the work in mathematics and analysis of Euler, the Bernoullis, d'Alembert, Lagrange, and Fourier. And this was very fundamental to his work in science. So over Helmholtz's career, he was able to make contributions to in a number of areas. Among his earliest work was work on conservation laws, electrodynamics, and acoustics. And also between 1855 and 1881, approximately, fluid dynamics, which is what we're going to be talking about. He also, as I said, did work in chemistry, which is somewhat less well known. He did work on thermodynamics, the least action principle, and free energies in the 1880s. And of course, the Helmholtz-Gibbs free energy and his work on entropy are well known, but somewhat less discussed as kind of fundamental results in philosophy. One of Helmholtz's first publications was on the conservation of force. And if you're following along in the paper, this is the beginning of section 2. So I am actually talking about the argument of the paper. And in this 1847 paper, he argued for general force conservation, not just of mechanical, but of dynamical forces. And of course, he uses the term force, but it's what we would now call energy, is what he's talking about. Although there's a lot more to be said about that, of course. And in his work, in his early work on force conservation and on forces and their application in general, as I say, Helmholtz drew on the work of Euler, Lagrange, and Bernoulli. So in his 1854 paper that's cited here, there's a long quotation which I can read. He says, "For all purely mechanical moving forces, all our machinery and apparatus generate no force, but simply yield up the power communicated to them by natural forces, falling water or moving wind, or the muscles of men and animals. After this law had been established by the great mathematicians of the last century, a perpetual motion, which should make use only of pure mechanical forces, could only be sought after by bewildered and ill-instructed people." There's a bit of condescension at the end there. So the reason that I mention this is that one of the most fundamental points that Helmholtz arrived at the beginning of his career, and that he never departed from, and that he used kind of almost as an article of faith, although he himself would disagree with that description of it, because he thought that it was very well justified, was that there can be no such thing as perpetual motion, and that there can be no such thing in particular as the creation of force, that force is always going to be conserved. And so this was a fundamental axiom that Helmholtz used throughout his career. He used it to argue against his enemy Weber in electromagnetism. He used it to argue against a number of in fact, this was behind his arguments against vitalism, is that he thought that vitalism appealed to perpetual motion and to the creation of force. So this was, again, very fundamental to his work. And in his early work in the 19th century, Helmholtz used fundamental results in mass and energy conservation in his work on fluid dynamics, electromagnetism, and optics. And it's important to note that, in fact, there's a way of explaining Helmholtz's work in fluid dynamics that's just almost as an application of the fundamental laws of fluid dynamics and energy or force conservation. And so there is a way of explaining Helmholtz's work, again, in fluids, in his analysis of the motion of fluids, where you would just say that he is, in a sense, applying earlier theoretical results in analysis and also in fluid dynamics. So where he's just applying the work of Euler and Lagrange, for instance, in fluids. And so one point that I want to make in this paper is that, in fact, while this is a very attractive way of looking at what Helmholtz was doing, there's much more to be said, because in particular, I think that kind of explanation misses out on what Helmholtz himself saw as a necessary condition for arguing for that kind of theoretical or law-based unification of fluid phenomena, for instance. And I think that one thing that you can argue for is that Helmholtz thought that proving a kind of systematic unification of the phenomena through experiment was necessary before you could argue for this kind of law-based unity, arguing that fluids, for instance, display general energy conservation, or that Euler's and Lagrange's laws apply in general. So Helmholtz's results do rely on the incompressible Euler equations, and they also rely on Lagrange's earlier results. But what I want to argue for, and what I've argued for in the paper, although, as I'm sure will be mentioned incompletely, is that Helmholtz's explanation of friction is important, in particular because he was able to derive all of the results of Euler's theory and all of the results of Lagrange's theory, but also to show that they applied to a number of experimentally verifiable phenomena. So that what he was doing was not just based on a kind of law-governed or theoretical explanation, but that he was also making a kind of deeper systematic argument about the experimental basis of what he was doing. So I want to look in particular at the case of friction and at some of Helmholtz's early work on this topic. So you might ask, why are we talking about friction if we're talking about fluid dynamics? But of course, so in Helmholtz's early work in fluid dynamics, mostly in the 1850s and 1860s, Helmholtz, along with many others in this subfield of science, analyzed turbulence in fluids. And here, fluids can mean a broad range of phenomena, as we'll talk about in a second. He analyzed turbulence in fluids as a kind of friction that arises between segments of the fluid. So with his theory of friction in fluid dynamics, Helmholtz proves a number of seminal results that involve applying the techniques of mathematical analysis to observed phenomena. And so in the analysis of Helmholtz's theory that follows, I want to emphasize that here he moved from systematic unification, which I'll say more about what I mean by this in a moment. But in the case of fluids, systematic unification means that friction is shown to be a measurable phenomenon that can be measured and interacted with in numerous experimental contexts. And I want to argue that Helmholtz moved from systematic unification to explanatory unification, in which friction is shown to be responsible for a broad range of effects. And so this explanatory unification is something closer to the sort of top-down or law-governed explanation that's often appealed to. So in his 1858 paper on vortex motion, which was really a seminal paper for him, Helmholtz studied several experimentally verified phenomena, which appeared to share a common set of observed regular motions. So it's, as I said earlier, sometimes when we talk about fluid mechanics, we think only about sort of water or other things that are usually considered to be fluids, but of course air is a fluid. Anything that behaves like a fluid, in a sense, can be analyzed as a fluid. So smoke rings, the motion of air around the ends of organ pipes, the wake of objects dragged through the water, even certain electromagnetic currents were analyzed as fluids in this tradition. And so Helmholtz mentions all of these phenomena as phenomena that can be produced in the laboratory or studied under experimentally controlled conditions at the time. So you can see from the pictures here, the one on the left, I think you can see on your left, is a set of smoke rings or smoke going through the air. And the one on the right is a wake in water that's made more obvious by, of course, this is ink showing the von Kalman avenue in water. And you can see that these two sets of fluid motions actually share certain characteristics. You can see that the motion seems similar in certain ways. And one of the things that Helmholtz is going to talk about is that the experimental investigations that were going on at the time of fluids showed that these types of phenomena were all similar, right? So this is the first thing that he points out in his 1858 paper, is that we can show experimentally that there are certain similar regular motions that these seemingly disparate phenomena all share. So Helmholtz himself was able to produce many of these effects in his own lab. And throughout his career, and this is something that I want to say is characteristic of his work, Helmholtz was able to produce effects in his lab that allowed him to control for certain regular motions or phenomena. And so something that's really important to his experimental method was to be able to show that he could produce a complex phenomenon by reproducing its conditions or whatever is necessary to create that phenomenon. So, for instance, in his studies of sound, Helmholtz showed that he could reduce complex sounds to primary vibrations and thus analyze these complex sounds into their components. And as a result, he was able to analyze complex phenomena, including harmony. And similarly, in the case of fluid motion, Helmholtz came up with experimental techniques and theoretical advances that allowed him to model complex fluid motions. But it also allowed him to give a new quantitative and even experimental account of friction. So here, friction is considered as a kind of complex phenomenon or result of components that all come together in order to produce this phenomenon. And so Helmholtz wants to argue that friction is produced in these disparate experimental contexts, right? So that the kind of turbulence that you see with the smoke in the air and the kind of turbulence that you see with the wake in the water share a certain experimental basis, right? That you can show that you can produce them in similar ways in the lab. And that they therefore can be analyzed as similar kinds of systems. Okay, so Helmholtz's mastery of the experimental context allowed him to demonstrate what I'm calling the systematic unity of the phenomena of friction, showing that they shared a common set of motions for which physical analogies could be drawn in practice. And I should say that Susan Sterrett's work on the idea of physically similar systems, which is a concept that she took from Edgar Buckingham, this is just an aside, is directly relevant. And Sterrett also talks about Helmholtz's work in this context. So if you, for a sort of much more rich and detailed presentation of how this works in Helmholtz's work, you can see Susan Sterrett's papers on similar systems. But it is nonetheless true, and I should say this, that Helmholtz's most striking result in fluid dynamics, fluid mechanics, involved what I'm calling explanatory unification, or what's often called explanatory unification. And this is the familiar account according to which we unify phenomena by showing that they can be analyzed using the same laws. And here this might simply mean physical laws. So one of the most important things that Helmholtz did was to show that actually, and this has been talked about in many, many papers, so I don't really have to, I'm not going to rederive this result here. I'm just going to mention that this is true, is that Helmholtz was able to unify the two extant theories that were used to evaluate fluid motion. And that was important partly because these two theories actually had two different substantive theories of fluids that were attached to them, and they were inconsistent with each other. So this is a well-known point. So Euler's equations for fluid motion, in particular, can be applied using the hypothesis that fluids are perfect continua, right? So Euler's equations for fluids are they kind of work in application in practice only if we assume that fluids are perfect continua. Lagrange's equations, on the other hand, require assuming that the fluids are granular, that fluids are made up of atomic particles. And so, as many people pointed out at the time, it's impossible for both of those things to be true at the same time, unless we consider that one of them is simply a model or an idealization, and the other is actually a true substantive description of fluids. And one of the things that's important, oh, sorry, I shouldn't have gone on to that slide yet. One of the things that's important about Helmholtz's method is that he pulled back somewhat from the question of whether fluids were continuous or granular. And he instead focused on the question, especially in his 1858 paper on vortex motions. He said, what is it that we are actually doing when we want to analyze fluid motion? One of the most important things we want to do is analyze phenomena like vortexes of fluids. And in particular, we want to analyze phenomena like friction and understand how they come to be. And so instead of focusing on the question of whether fluids really are perfect continua or whether they really are granular, the first thing that Helmholtz did was to ask the question, how do we analyze vortex motion in fluids? And so how can we show that Euler's and Lagrange's equations are applicable to these fluid motions that are really our target, that are really the thing that we want to explain? And so Helmholtz's goal in the paper was to show that the interaction of rotating sheets of fluid produces friction. So he wanted to show that if we can give an explanation of how rotating sheets of fluid interact, and if that explanation can then cover all of these phenomena that are produced in the lab, that are produced experimentally, and we can show then that these fluid motions actually give rise to turbulence or friction that give rise to the phenomena that we observe, then that is going to actually provide the kind of systematic account that Helmholtz thinks is important in the first instance to explain what's going on in the case of these phenomena like turbulence and vortex motion in fluids. So the first point was to be able to measure friction and turbulence specifically. But the other idea was for Helmholtz to be able to give what we would now call a model of the underlying rotational motion of the fluids, so that friction could be modeled as an effect, and the motion of the fluids could be modeled as the interaction, the thing that gives rise to the effect. And it's really important to stop and notice here that before this 1858 paper, and I don't think that I'm saying anything particularly controversial here. It actually wasn't very easy to measure friction. And so one of the things that's quite striking and noticeable about this paper is its kind of law-governed unification, which we'll talk about more in a moment. But one of the most fundamental points about it is that Helmholtz made friction measurable by showing that the interaction of rotating sheets of fluid produces friction as an effect. It's the cause of friction. And so because he was able to do that, he was able to show how friction can be measured. And I'm going to say something about that in a moment, but that's the basic idea. And one of the points that I want to make is that is in and of itself an interesting point, that while people usually talk about this paper as Helmholtz's 1858 paper as displaying a kind of law-governed unity in the fluid phenomena and kind of unifying the explanations of fluids, I wanted to point out that, in fact, one of the most fundamental results of that paper has nothing to do with that, and it really just has to do with how Helmholtz was able to show that these phenomena of fluid motion and turbulence, in fact, have a deep underlying unity. So how was Helmholtz able to show that fluid motion is measurable, that friction is measurable? He introduced these concepts of vorticity, vortex lines, and vortex filaments. And so the vorticity of a fluid, and this is just a sort of scientific diagram that I stole from someone that basically illustrates these concepts. So this is a vortex filament. So this is, if you take a fluid, the idea behind Helmholtz's model of fluids is that all fluids are made up of filaments of this kind. So you can take let's say, a river, and you can show that that river is made up of a set of, and of course these don't really exist, right? But ideally, in an idealized model, that the river can be divided up into vortex filaments that are all kind of flowing next to each other. And so we imagine tubes of fluids. And there are two ways of describing the motion of the fluid through the tube. So there's the vorticity of a fluid, which is its average rotation within a given region. So we can talk about the vorticity within the vortex line or the vortex filament. And the vortex line is the tangent to the vorticity of a fluid at a single point. So we might say, so this is just a way of introducing a concept that allows for the mathematical measurement of the vorticity of the fluid. And so, but a vortex filament is vortex filaments or vortices is really the fundamental concept of Helmholtz's model of fluid motion. So the idea is you imagine a tube of fluid with a certain vorticity and a certain circulation of water through the fluid. Now, the important point that happens here is that you reduce the diameter, you theoretically reduce the diameter of this tube to a limit. So you say, let's imagine that the diameter of this tube can be reduced almost to infinity, right? So to a limit, as in calculus, and you hold the circulation constant. And so what you end up with is a fluid that's modeled as being composed of these vortices, which allow for the measurement of the circulation or the rotation of the fluid within this tiny region. Okay, and so the idea is that the total fluid can be modeled as, of course, adding up all of the vortices in a particular region. So here's what Helmholtz did. He provided this idealized model of the vortex filaments or vortices of a fluid, and he showed that you can construct an experimental model where you show how there is an interaction between vortices and what he called vortex sheets and vortex rings, which are just sheets of fluids and rings like smoke rings. And he showed in experiment that all of the observed frictional effects that he had mentioned in the beginning of the paper could be produced by the interaction between these three. So I'm obviously having to simplify quite a bit, right? But the idea is that this idealized model of vortex filaments or vortices allows us to use the usual instruments of calculus and so forth to measure the vorticity or average rotation or circulation of the fluid, whatever it is that you want to measure. And then if you can show that vorticity is actually a result of interaction between vortices, vortex sheets, and vortex rings, and we can measure and model all of those, then you can break friction effects, you can break turbulence down into all of those different components and show that friction and turbulence are actually can be modeled and measured in these terms. And so this is a very complicated argument. And of course, as is well known, Helmholtz didn't entirely show turbulence is still a problem, right, in fluid dynamics, but Helmholtz was able to show that at a very basic level, we can model friction in fluids as an effect that emerges from these more fundamental components. Now, one of the things that's very important here is that, of course, Euler and Lagrange both tried to model friction in their theories of fluids. And others who were in the Eulerian and Lagrangian traditions had tried to do that also. And they had not succeeded very well. So they weren't really able to systematically apply either the Euler equations or the Lagrange equations to fluids to show how to measure friction. So Helmholtz's paper is really a landmark result in the history of science because he was able to show how this could be done. And one thing that's really important, I think, is that if you read the 1858 paper, What Helmholtz importantly does not do is say, let's start with Euler's laws and Lagrange's laws and see what we can derive from them. Instead, he says, let's look at how we can systematically produce the phenomena of friction from an idealized model and then what we know about experimental phenomena. So if we can investigate what's going on in fluids by looking at how the different elements of fluid motion are produced experimentally, and then find a way of measuring those phenomena, including friction, and show how the phenomena that we have access to in experiment can be modeled as effects of underlying causes that we know about. And in particular, Helmholtz's theory can model friction quantitatively as arising from the interaction of fluids and even solids in motion. But Lagrange's and Euler's theories famously have to treat friction as an observed constant. So they just say, let's take friction to be, F and see whether we can measure it. And famously, it was very difficult to do. So, of course, Olivier Derigal's work is very excellent here in his work on the history of fluid dynamics. So Helmholtz's account is a perfect example of a theory that can account for all of the old results. So he can derive all of the theorems of Lagrange's and Euler's theories, but he's also able to give a novel explanation of friction that wasn't available in either of those theories. So there are a couple of points about Helmholtz's theory of vortex motion presented in 1858 that I want to emphasize. One is a point that's often made, which is that Helmholtz's theory proves all the theorems of Lagrange's and Euler's theories, or at least he doesn't do that in the paper, but it's possible to derive all of Euler's and Lagrange's results from Helmholtz's account. But you can prove more in addition. And you can, in fact, explain more with Helmholtz's theory than one could with just Euler's and Lagrange's. Helmholtz's explanation incorporates relevant experimental data from related research. So he looked at wave research in acoustics, for example, and looked at how it was related to work in fluids. But the important point, and here I'm actually drawing again from Olivier Derigal's work, Helmholtz's new explanation gives a quantitative derivation of the friction effect as an interaction between fluids. And this was new. So Helmholtz's account doesn't just conserve a broad spectrum of experimental results, it gives a novel quantitative explanation of an observed phenomenon. So these points on this last slide are all reasons, as I say in the paper, so we're getting more towards the end of the paper, these are all reasons for giving epistemic assent to Helmholtz's theory, right? That he was able to account for the results of earlier theories, that he was able to incorporate data from related research, and that he was able to explain a phenomenon in terms of simpler components giving rise to that phenomenon. So there are rational grounds for accepting Helmholtz's theory, but there are also grounds for skepticism about the claims that make up the theory. So remember when we were talking about vortex filaments or vortices, in order to model fluid motion, Helmholtz had to make the idealizing assumption that a vortex filament, the diameter of a vortex filament can be reduced beyond any limit, right? So that it can be reduced without any bound, right? And that requires making the idealizing assumption that fluids are perfect continua, right? Because if fluids are granular, then you can't make that assumption. And that assumption's necessary in order to apply the techniques of calculus that Helmholtz wants to apply. So in particular, without that assumption, you can't guarantee the existence of a unique vortex filament for each neighborhood of a fluid. And without that assumption, Helmholtz's model doesn't work. So this is, of course, depending on whose theory of fluids you accept, this might be considered to be an idealization. If you're Lagrange, for instance, and you think that fluids are granular, then you want to argue that this idealizing assumption doesn't actually describe fluids as they really are. If you're Euler, then maybe you want to say that this is correct because you want to say that fluids are continuous. And in fact, one of the things that I want to point out is that so nowadays people argue that the best empirical evidence suggests that fluids are actually granular. And in fact, Helmholtz himself used elements from Lagrange's theory in his own proof. And so he used elements of both theories kind of eclectically in coming up with his model of fluid motion. And so interestingly, Helmholtz's theory is a kind of mixture of the account of theory of fluids according to which they're perfect continua and the account of theory of fluids, according to which they're granular. And so you can say that there are rational grounds for accepting Helmholtz's theory over Euler's or Lagrange's, but because these elements actually make their way into Helmholtz's theory, there's not really grounds for accepting each of the kind of implicit substantive claims of Helmholtz's theory because it's kind of a combination of various idealizing assumptions and statements about what makes up fluids and so forth. And so it seems like while Helmholtz's theory works on the level of providing a basis for measurement and also providing a kind of law-governed explanation, it doesn't seem to work as a physical explanation, as a substantive explanation. But what I want to point out, and I really do think that this is important for Helmholtz, is that he wasn't really aiming to give a kind of substantive explanation of fluids in his theory in the way that people often might consider. So he wasn't trying to answer the question, are fluids granular or are fluids perfect continua in reality, right? Are they really this way or are they really that way? That wasn't actually the question he was trying to answer. It's not that he didn't think that that question was important, but that wasn't the question that he was trying to answer in his paper. So what I think that he was trying to do in the paper was achieve two different goals for unification. First of the theory of fluids, but also for unification of the phenomena that he mentioned at the beginning of his paper. So here I'm going to reverse the order on this slide. So I think that, first of all, it's very clear, and this has been mentioned by many, many commentators about this paper, that Helmholtz was trying to achieve a kind of law-governed or explanatory unification. So the first thing that he was trying to do, this is clear and is well known, was that he was trying to show that the fluid phenomena he was analyzing can be unified in the terms of the requirements for building a comprehensive system of nature under causal law. So this is a kind of top-down or axiomatic or principled explanation. And of course, Helmholtz wanted to argue in particular that you can build a theory of fluids for which both Euler's and Lagrange's theories can be shown to be kind of special cases, right? So he was able to show that all of the theories of fluids actually can be unified under one heading, and that there can be a single set of laws of fluid motion. And so that was a really fundamental and important result. But what I want to point out is that Helmholtz's second goal for the paper was not to give a substantive account of what fluids really are. Are they really continua? Are they really granular? Instead, what he wanted to do was to achieve this goal of systematic unification. And in my view, systematic unification works to make concepts measurable and observable and to build scientific systems using those concepts and to show that they can be related to each other experimentally, not just theoretically. So in particular, the concept of friction, which in Euler's and Lagrange's theory, again, was used just as an observable constant to talk about just, modeled as just kind of a variable in their theory. Helmholtz was able to go much deeper and to show that friction could be produced in experimental contexts, and that it also could be analyzed into its simpler components. So this is, and that therefore one could show that it's measurable and observable but also that it's producible in the lab, right? So that you can show that, for instance, turbulence can be produced in the lab from a certain set of actions in an experimental context. So systematic unification is a constructive or bottom-up method that uses observable, measurable phenomena to construct scientific theories or systematic explanations. But explanatory unification begins from a broader commitment to the comprehensibility of nature in terms of causal law. So it's this kind of law-governed explanation. So I realize, and I'm sure I'll be pushed on this, that this is a kind of rough and ready distinction, but I do think that something like this has to be what's going on in Helmholtz's work. So, as many others have noted, Helmholtz's great contributions included the synthesis of diverse areas of knowledge, and he was able to build broad explanatory systems. But he is able, in the case of friction, to give a real definition of friction that showed that it was a measurable phenomenon. And as a constructive theory of fluids, this isn't necessarily successful, right? So he's not necessarily able to show that fluids are composed of a certain substance or something like that, or that they're fundamentally granular or fundamentally continuous. But he is able to show that fluids and fluid motions can be modeled in a certain, using a certain common set of assumptions. So one question might be, are we able to simply abandon explanatory unification and just focus on this systematic goal for science, on building better systematic theories? And so the last point I want to make is that it's not that I want to argue that Helmholtz's experimental goals or his goals for making the phenomena measurable are somehow more fundamental than his goal of unifying nature under causal law. I want to argue that these are both fundamental aspects of his approach. So we can't simply say, well, we want to throw away this goal of unifying nature under causal law, and instead we want to look at whatever we can sort of measure and probe in experiment. Helmholtz wants to argue that, in fact, without the ability to model and describe phenomena in terms of causal law, Helmholtz wants to argue we don't actually have access to experimental facts, right? So explanatory unification, and I realize this is very quick, but I want to make sure this point gets in. With explanatory unification is actually necessary in order to achieve systematic unification. So one key example of this is that Helmholtz's account of the fundamental laws of fluid motion in terms of vortices or vortex filaments is an explanatory theory that's used in order to achieve a systematic explanation of friction. And so in particular, law-governed explanations might be used in systematic explanations, and so one of them can't be divorced from the other, but they are separate things. So Helmholtz's view, I think, contains an intriguing insight. We have access to the detailed systems of science, even in experimental contexts, only if we build broader causal explanations that may or may not correspond directly with the phenomena at a fine grain. So ultimately, Helmholtz's realism is accessible only through this idealist, or probably better, idealizing route. Thanks.
So thank you, Professor Lydia Patton. We'll now begin a discussion with Lucas Baccarat. So, Lucas. Sure.
Can you hear me? Yeah? Okay, cool. So thank you, Professor Lydia Patton, for the wonderful talk. It is really an honor to be commenting on your paper. Unfortunately, I'm not a specialist in Helmholtz, but I'll try my best to pose questions. They might sound naive, I guess. But one thing that I noticed that it's a bit different from your talk and your paper is that there is a greater emphasis in your paper in the transition from only caring about systematic unification to explanatory unification. And explanatory unification, at least in the paper, shows itself to be the great novelty between Helmholtz's earlier work and his later work. So my question actually concerns that, because I think that the paper shows, even though you said it was quite sketchy, the distinction between the two kinds of unification, I think that it does become very clear. But my larger philosophical question would be, what actually motivated such a difference in approach from only systematic unification to explanatory unification? So you do give us a hint about what it could be, which is a greater commitment to comprehensibility, and in the terms of Daniel, which is a greater commitment to explaining phenomena in terms of causal relations. And I was wondering if there is anything, if that is related to a change in his conception of causality in itself. Because in the 1980s, I guess, when commenting on the introduction to the On the Conservation of Laws, on the conservation of energy, Helmholtz does state that he had a much more Kantian account of causality in his earlier career, and then it changed throughout his career for a more phenomenal kind of causality, I guess. I quote Helmholtz here. He said to page 13, the philosophical discussions of the introduction were more strongly influenced by Kant's epistemological views than I would now like to recognize as still correct. It only later became clear to me that the principle of causality, in fact, is nothing but the assumption of the lawfulness of all natural phenomena. He then goes on to say that he some sort of differences, but it basically is that there is a lawfulness within all natural phenomena. I believe that he was postulated that Kant understood causality in terms of numenical causality, as Gregor Schumann later says. So that would be my first question. Would you like to answer to that now, and that, or would you like me to pose all of my questions, not many, and then?
It's whichever way you would prefer. It sounds like, yeah.
No, so you can answer this one, and then I'll make a new one. Maybe you already answered it. So.
No. No, I doubt it. So I'm very glad that you mentioned Gregor Schumann's work, because I think that's really key in understanding this shift. And I think the shift that you point out is very important, because so in the 1847 pamphlet, I guess, on the conservation of force, it's true that Helmholtz does talk about the a priori or transcendental presupposition of the causal law as being necessary. And in particular, he argues early on, and Schumann's work is again very good on this. There's a book that he has called "The Loss of World in the Image." That's a very very detailed presentation of this, way more detailed than I'll be able to give right now. But the idea behind this shift that Schumann points out is that early on, Helmholtz is really is at least partly committed to the idea that we have to assume some set of a priori causal laws in order to promote what Olivier Derigal has called his notion of the comprehensibility of phenomena. And I think I mentioned this in the beginning section of this paper. And the idea there is that there's a certain set of causal laws that have to be assumed in order to make sense of the universe as being governed by, a single set of laws. And so that's a very strong assumption, and that, in fact, does add up to a kind of a priorism or almost neo-Kantianism. And of course, the neo-Kantian commentators at the time kind of seized on that, like Hermann Cohen and others talked about Helmholtz as being a kind of ally to their cause. And that was a much stronger view. Later on, Helmholtz, as you say, and there have been a number of commentators who have pointed this out, he moves more to the idea that there has to be some causal explanation of the phenomena, right? So some set of laws from which we can recover the phenomena, but that there doesn't necessarily have to be, uh, how should I put this, a substantive postulate about the unification of all of those phenomena under the laws, right? So that just there has to be some set of laws, and there has to be some explanation of the phenomena, but that set of laws doesn't have to imply some kind of, as you say, some sort of like noumenal explanation of how things are. I think that, you know, some Kantians would say, well, Kant doesn't think that there's noumenal causality either, right? But I think that Helmholtz's later work has much more of a loose fit between the causal laws or the causal presuppositions, and simply his idea that there has to be some kind of presumption of law-governed explanation in order for science to work. So I think, just to sum up, like the key shift is between early on, there have to be specific laws, I think he thinks, that have to be presumed, and we have to assume that there's a system of nature that's kind of that's governed by a set of laws, and that nature has to be comprehensible in law-governed terms. Later on, Helmholtz allows for the possibility that, for instance, there could be inconsistent sets of laws. And I think that's a very important shift, and that's what Schumann has really focused on, is this idea that the world doesn't necessarily have to be, in the later Helmholtz, maybe past, it depends, but 1860, 1870, the world doesn't necessarily have to be comprehensible in terms of a single set of consistent causal laws, I think is the move later. Yeah.
Cool. But just to make it clear, so you don't think it bears any relevance to the shift from systematic to explanatory unification? Just
No, okay, sorry. I'm sorry, I should have said something about that. Yeah. Sorry. So I think that, look, so I think in 1840, I think that explanatory unification is fundamental for Helmholtz throughout his career. And I think this is one so like in 1847, clearly that's an explanatory unification project, right? The conservation of force paper. But I think that systematic unification, one thing that gets missed about Helmholtz's work is that he does think that that laws of nature are necessary to be able to probe the phenomena in experiment, right? So explanatory unification is necessary for systematic unification. But I think that the shift comes about when he realizes that systematic unification later on, I think he thinks, is actually more fundamental. So I'm glad you pointed this out, because I think that really is something that I'm at least medium willing to defend. That I think in his later career after the 1860s, what Helmholtz is arguing, and I think maybe you pointed towards this rightly so, is that the necessity for systematic unification is in a sense more fundamental, because what we want is the comprehensibility of nature, and what we want, like that's what he wanted for the law-governed explanation of nature, right? What we want is to be able to comprehend nature as a system that can be investigated experimentally as a set of interconnected phenomena. And early on, he was again more Kantian. He thought that, you know, a single set of causal laws was necessary to that project. And I think that as he moved on in his career, he came to the conclusion that systematic unification in the way that I've just described is actually more fundamental than explanatory unification, and that if we have to let one of them go, it's that second one. It's the idea of a single consistent set of causal laws that make consistent substantive claims. I think he thought that experiment was more fundamental. Being able to probe the phenomena and understand what's going on was more fundamental. And if that required inconsistent systems of laws, then so be it. And I think that this paper actually may have been, in a sense, a turning point in that regard. Thank
Okay,
you.
great.
Very
So
insightful.
that already answers my second question. So amazing. Thank you very much. The last one is just it's a clarification point, actually. So in the paper, unlike in the presentation, you do try to elaborate a little bit more on how these unification projects bear some kind of relation to the scientific realism issue. So, and at the very end of your paper, you state that after trying to develop the whole how the both kind of unifications bear a relation to the issue, you say that we have this Helmholtz fields containing an intriguing insight. We have access to the detailed systems of science in some cases only if you build broader casual explanations that may or may not correspond directly with observable, measurable phenomena at fine grain. Ultimately, Helmholtz realism is accessible only through an idealist route. And I would like you to further comment on it. So just to explain, and once again, just since the presentation didn't really touch on this topic, how it all relates to the scientific realism issue.
Right. Yes. So I apologize for not reading the paper, but I know sometimes that can get a bit long. So thank you for bringing this up. Yes, and I did briefly mention it, but I didn't go into it very much. Partly because I know it's that's a bold claim. Actually, I was a little nervous even when I wrote it. So you're right to pick up on this exactly. Okay, so here's what I meant when I was talking about that about what Helmholtz is doing here, right? So I've said before that he doesn't think that we can. That I think that these are both whatever you want to call them, right? Law-governed unity and experimental unity, explanatory and systematic, however you want to parse it. I think that both of these are fundamental to his work. And I think that throughout his career, Helmholtz is committed to both of them. It's just a matter of, as we just discussed, the strength of his commitment on one side or the other, and what exactly he thought that commitment consisted of. And I think this is a really good question, because it's partly the question of, as your first question picked up on, what Helmholtz meant by law-governed unification, or what I called explanatory unification, changed over his career. Did he think that it involved certain substantive posits about underlying reality, right? And I also talk about that in the paper, in this distinction that Haider has emphasized between topogeneous and hylogeneous factors in experience and so forth. And I think that one of the results of Helmholtz's shift away from arguing that there has to be a single consistent set of natural laws, right, of causal laws, is that he also shifts away from the idea that there has to be a single consistent explanation of the phenomena. And so I think that, and I think that that is one element where I think that Helmholtz moves away from a certain kind of scientific realism in his later work, that he had maybe been at least tepidly committed to earlier in his career, right? So that earlier on, he had this strong principle of the comprehensibility of nature, where he argued that we can use scientific laws to probe and to explain natural phenomena, and that and Gary Hatfield has actually argued that during this period, Helmholtz was a kind of structural realist. And that he argued that anything that we can prove as a scientific law, in fact, does correspond to reality, or at least that we have some reason to assert that it corresponds to reality. And I think that it's very possible, and I certainly wouldn't want to go up against Gary Hatfield. I think that it's very possible that that Helmholtz was committed to some such position, at least up until the late 1850s. But I think that after that, he does seem, at least in a lot of places, to argue, and I think Schumann is right here, to argue that what's fundamental to giving a systematic picture of the phenomena is just being able to give that picture, right? Is just being able to sort of systematically investigate the phenomena. And so I think that here, what's really important to Helmholtz is less our commitment to some set of real objects beyond the phenomena, and more our commitment to the bare idea of the comprehensibility of the phenomena, of our being able to understand the phenomena and investigate them. And I think that he becomes less and less concerned with what there is outside our investigation. And so I think that he just has a much more, in his later work, he has a much more practical orientation, and argues that really the experimental method is what's fundamental to science, and that even our explanation in terms of causal law is important mostly to being able to understand phenomena through experimental investigation, rather than using the causal laws, for instance, as descriptions of reality. And I think that this is sort of cheating, but I think that all of the evidence that Schumann has presented goes in that direction. But I also think that one can give an argument based on things like his explanation of friction in the 1858 paper, where he says, I think that fluids are granular or can be, investigated using the atomic theory. But I also think that we have to make this assumption when we're giving the law-governed explanation that they're perfect continua. And there's a similar argument that can be made in terms of Helmholtz's account of electrodynamics around the same time. And I won't go into that, but again, there's a difference between his substantive theory of electrodynamics and his law-governed theory. Sorry, that was a lot, but
no, it wasn't. Thank you very much for your replies. That was all I had to ask. So thank you very, very, very much.
Oh, thank you.
So I would like to thank you both for the discussion. We'll now open a question session, and now I would like to welcome Professor Mark Textor, Peter Simons, and Thomas Übel. So there will be the opportunity for them to ask questions and also our audience. But first of all, I would like to know if Professor Textor, Übel, or Simons have any questions to pose. No? Okay. Übel? Yeah?
Okay.
Oh, yeah, you're muted.
Yes.
Yes.
Well, thank you very much, Bruno. First of all, thank you very much, Lydia, for this fascinating talk about Helmholtz and these two conceptions of unity. In my talk yesterday, I was talking, of course, about Viena Circle and unity of science there, and I brought up Neurath's conception of unity of science, which he preferred to call encyclopedic unity, the encyclopedia. And basically what that is, what that involves is a sort of rejection of the model of a hierarchical, of a hierarchy of various disciplines, sciences that are reductively related, etc., that kind of stuff. And then, well, Neurath doesn't really, as far as I can see, he doesn't give much by way of historical antecedents to this view. He sort of sees it more like it's more, or it comes across in his writings more like more as a reaction against what he sees as possibly sort of formalist excesses of too much reduction, etc., etc. But hearing you speak about the two conceptions of Helmholtz he has of unity, I couldn't help but wonder whether what you call systematic unification isn't in some sense well, I'm not drawing a connection between them, but whether a direct connection between Helmholtz and Neurath, but whether the idea is not somewhat similar in as much as you characterized it, that what's at issue in systematic unity is to establish measurable relationships between phenomena. And one of the things that Neurath sort of says is that was really crucial for his encyclopedic unity was to have what he called establish cross connections between phenomena that different disciplines, different theories treat with. And well, I was wondering, can you, what do you make of the possible parallel there, or possible, similarity of ideas there? Does that strike you as?
Absolutely, thank you. And yes, and I think that I wondered about this because, of course, when you talk about unification, this is the first thing that comes to mind is unity of science, and and of course that was a bit later. And so then you wonder, to what extent was one an influence on the other? And I think that certainly Helmholtz, it's kind of interesting. So I should say this as a sort of background point. It is very interesting to try to establish whom Helmholtz influenced, because at some point he became so ubiquitous in certain German contexts in particular, that it would have been possible to be influenced by his ideas without ever actually necessarily even reading anything that he had written.
Right.
Because, yeah, and so it's very difficult historically because Helmholtz was just there. Yeah, I mean, so for instance, in the lab in Berlin, so David Kahan's work on Helmholtz is really important here, because he talks about the his lab, and then later his work at the Berlin Academy, and he just became so he became kind of the the Darth Vader of German science. That's a terrible analogy, but it's like, but he became so sort of the head of an empire in a way of his research. And so it's actually kind of difficult. Sometimes I see work by others, and so this is a prefatory remark to I see work by other people, and I think, well, this sounds like Helmholtz, but there's no way to know. But there's no proof that this person ever read Helmholtz. But they could have heard about it from Hertz. They could have heard about it from Boltzmann. They could have heard about, there's any number of more, Dubois-Reymond, all of the people who Helmholtz was working with. And so it's difficult to know. But having said that, I think you would know better than I would whether Neurath had read Helmholtz.
He probably read him at some point, and he will have, and he studied Mach quite intensively. So obviously there's at least a reflection of Helmholtz that comes through that. So yeah.
Yeah, and that would have been my guess too, is that this was really a case where it sort of filtered through Mach. And I think that connection would be what I would really want to pinpoint is, I think Mach, what he talks about is his account of causal law is much more minimal than Helmholtz's, because even though, as Lucas Baccarat has very well pointed out, Helmholtz's account of causal law kind of becomes less and less robust over time. He still never becomes a Machian, right? So he's still got a much stronger account of causal law than Mach does. And so I think that, but I think that nonetheless, what would then be, not to be egotistic about my point here, but I think that the concept of systematic unification then would become actually very important, like distinguishing these two then would become very important in terms of drawing a connection between Mach and Helmholtz. Because I think in terms of law-governed unification, Helmholtz is obviously very different. but I think they have a similar commitment to
nice.
whatever is necessary to constructing an empirical experimental
yeah.
picture and connecting these kind of systematic connections between, you know, so I think that actually making that distinction could be very helpful.
Yes.
In that regard, because there's a clear argument to be made that Mach and Helmholtz disagree about causal law. There's no question about that. But I think that in terms of systematic unification, they actually agree quite a bit. So then that would be what would influence Neurath, and then he wouldn't necessarily even, as I say, he wouldn't necessarily even have known.
That's right.
that was Helmholtz, but it would have come to him through Mach and through reading him.
Fascinating. Thank you. That's great. That's very helpful. Thank you.
Thanks very much.
Thank you, guys. Does anyone have any more questions here in StreamYard? Okay, so does anyone from the audience? Peter. Oh, sorry, Peter. Yeah. So yeah.
Thank you for the talk. Super. Lots of information. One of the things, I mean, I've read very little Helmholtz, but one of the things I have read is his stuff, relatively late stuff on quantities. And I wondered to what extent this very philosophical reflections on quantities derive from the way in which he dealt with physical phenomena in his actual physics. You know, I mean, these are the reflections of a very mature and very capable person. You know, they're not some sort of teenage fantasy or anything. So I just wondered if you could trace a line back to, for instance, the way he dealt with vortices.
Right. So that's right. So I think that this is fascinating work, the work that he does later on measurement and quantity. And so I should say, I think that the work that Matthias Neuber and Francesca Biagioli has done on this has been really fascinating. And I think it's pointed to some of the connections between, because it's historical work that they've done. And it has pointed, I think, to some of the connections between Helmholtz's empirical or experimental method and his work on measurement. And so it can seem that the arguments about measurement are purely mathematical, for instance. So he talks about the necessity of establishing an ordered field in order to make certain measurements and so forth. But I think that you can find connections. You can think of this as a kind of abstract reflection on his experimental career. That would be one way to look at his later work on measurement. Because you could say, for instance, he's looking at the sort of higher level conditions for making a certain quantitative measurement. But by that time, as you say, he's not early in his career. He's done quite a bit of experimental work. And so he's reflecting, one could make the argument, and I think that this work that I mentioned does make this argument, that his reflections on measurement are informed by his earlier experimental practices. And I think that's a strong argument to make for, and I think the ordered field argument, for instance, is a key place there, where he talks about that, of course, in order to make a certain measurement, you have to be able to establish an ordered field first. And so you could make a kind of strongly a priorist argument and say that this is a kind of Kantian transcendental condition and so forth. And I think Biagioli, to be fair, does make that argument, or something like it. But I think that you can also say that quite a bit of Helmholtz's earlier work in experiment establishes kind of conditions for being able to establish an ordered field, for instance, in a given experimental context. And so I think that when he talks about the conditions, they're not just a priori conditions, they're also in some cases empirical conditions. But I think that the two kind of work together, as I say, that you need a priori reasoning in order to be able to probe certain experimental contexts. And that's where it gets complicated.
Okay, well, thank you. Yeah, that's very helpful.
Thanks.
So does anyone from the audience? Okay, so Professor André. Ah, tá bom.
That's the microphone. Okay, Professor Patton, thank you for this very stimulating talk. After the unity of science, the first things that come to mind maybe is the Ernst Nagel model of theoretical reduction, when a set of empirical laws are reduced to more powerful theories. This usually corresponds to a deepening of our understanding of how the nature works, because we are able to explain with a smaller set of laws the same phenomena, the same class of phenomena. But Nagel model is very does not have an application in many others situations and for other science, like biology, for instance. Biology does not works with laws, but rather with concepts and models. For instance, the model of the synthesis of protein. Then my question is, Helmholtz was an incredible thinker with interest in many subjects. My son studies music in Conservatoire here in Brazil. And in the library of the Conservatoire, I found by chance Helmholtz books on musicology. And so he described the physiology of hearing and things like that. So my question is, does he have thought about the possibility to extend his notion of explanatory unification to other science like biology? That would be my question.
Okay, thank you. Yes, that's excellent. I think that's an excellent point to make about Helmholtz's methodology, because so the first thing I would want to say is that what the view that he had earlier in his career, and again, as the Lucas Baccarat has pointed out rightly, the view that he had early on was closer to something like a Nagel style view, that we can explain the phenomena in terms of a sort of increasingly minimal set of causal laws. And that we can then consider those to be, in some sense, a description of the way the world works, or something like that, right? And that we can reduce measurable phenomena to law, and vice versa, I think would be a reasonable description of his early work. But I think that as time went by, and as he started to try to give unifying accounts of more and more diverse phenomena, right? So as you say, he started talking about, he had the theory of sound and acoustic phenomena. He had theory of optics, electrodynamics, and so on. And so as he tried to kind of broaden his grasp of a larger and larger set of phenomena, in some ways, not surprisingly, he became less optimistic about the possibility, right, of finding a single set of causal laws that we could just derive everything else from. So I think that I think in the 19th century, that project would actually have been associated more with somebody like Auguste Comte and the positivist project. And I think that he just, or Kant, right? There's always Kant. But I think that as he went on, he realized that that project was becoming less and less plausible, given that, the laws that he was finding were leading in different directions. So I don't think that Helmholtz, so with a caveat, he never really did what we would call biology. Having said that, his PhD was actually in medicine. So that he was one of the first people whose parents told him that he needed to get a medical degree for practical reasons. He wanted to be a physicist, and his father told him, no, you're going to be a doctor. And so he got a degree in medicine, but then he started doing research in physiology, and then he moved it to research in physics. So he got to do what he wanted in the end. But the reason that I'm saying that is that he investigated quite a few phenomena, as you've noted, from both of those sides. So for instance, the theory of sound book is very notable for the fact that he starts with an investigation of the physiology of sound and how we perceive it. And then he goes on to talking about the mathematical and physical laws, but that describe acoustic phenomena. But it's also, and I think this is really where I would point out that, it's also true that he says that we need to know the acoustic laws in order to properly probe the experimental phenomena. And I think that's something that you don't ever find in some of these accounts that put laws at the basis, is this deep connection between the idea of an empirical explanation or empirical investigation and the idea of subsuming the phenomena under causal law, and this practical orientation where he says the laws are really useful in order to probe or investigate the phenomena. And so he had this deep knowledge of the physiology of perception in a number of respects, in optics and acoustics and so forth. And I think that his approach is very noticeable in the sense that it connects the experimental method and the method of subsumption under law very fundamentally, so that these really, one can't be understood without the other. And so I think that some of I don't know Nagel incredibly well, but I think that would be a disanalogy, is that, but I want to stop there because I don't know Nagel all that well, so I don't want to say something that's wrong. But yeah. Thank you very much.
Thank you. We have time for more questions. So, Professor Ingo. You can hold it, or you can.
So it looks nice.
Can you hear us?
Can you hear me?
Yes.
Yeah, it's fine. Okay, good. Yeah, thanks very much. It was a very inspiring talk for me, because I think we have also the unity, so to speak, of mathematics, explanation, and measurement from my point of view. And my question, because I'm mainly interested in logic and philosophy of language and so on, I put my point to a relation between mathematics and what you call explanation. So let me mention at the beginning that you say something like, we can reconstruct Helmholtz's conception in such a way that we can prove using Helmholtz theory, or we can prove all theorems of Lagrange and Euler using his theory. So we have this concept of theorem in that. So we can, maybe a theorem is connected to mathematics. And then you say the next thing was, and more besides. I think it was on your slide, and more besides. And the more besides can be, from my point of view, something like a model of mathematics, like in logic. You get a model of logic, and the other one is connected maybe with measurement, so the other component of this more. And there was another remark saying that friction, which I call a logical form of friction in Euler and Lagrange, is like a variable. So it is kind of atomic sign in here. And Helmholtz had the idea that friction is a kind of structure. You're kind of speaking about analyzable. And if you go to logic, for example, the simplest case would be propositional logic, propositional classical logic. You have one sign, you have a propositional variable like p, and try to find a model, you need at least two values. So you need a more complex structure for the same thing. So in a sense, if you go, so to speak, from a syntactic understanding of logic, if you try to connect this concept theorem to syntax, maybe it's a modern, it's Hilbert style thinking, then you have maybe some unstructured thing. And if you go to model, you can have a very complex structure in relation to, or is a kind of interpretation of this sign. So then it comes to my mind that creating a model, in a sense, is in this formal direction very similar to getting a kind of explanation. You can look at a model, or maybe give an interpretation or semantics to understand things. So, for example, in logic, in modern development, was a case that we have an uninterpreted calculi with respect to model logic. And when you got the CRIP result, it was much later, very decades later, to get an, so to speak, an understanding what this is, if you have this concept of a model with possible worlds in it, and a reachability or accessibility relation in it, and so on. So in a sense, we can look at this kind of model not only as a syntax, maybe with respect to the basic understanding of what necessity and possibility is, but as a kind of explanation of that. Or in a very general case, we can say if we have, for example, consistent but maybe incomplete models of something, it can be such things as an explanation. So, my general question is if you would accept that there is a kind of relation between creating, so to speak, models with respect to logic as a kind of explanation. And if is this a possibility to read, so to speak, Helmholtz's work, to have this new understanding of friction as a kind of looking for an interpretation or a kind of model with respect to a physical background?
Okay. Yes, that's excellent. So that's an excellent question. I have, and it partly because it points to an interesting historical trajectory, right? So you mentioned Hilbert, and so there is actually, and I'm very far from the first person to point this out. There's a direct historical trajectory from Helmholtz to Hilbert through Heinrich Hertz, right? So there's Helmholtz talks about okay. This gets very complicated very quickly. But Helmholtz talks about theories as and even perceptions as being signs. So he has what's called the sign theory, Zeichen theory. And so he talks about sensations, for instance, as being signs and not copies of their of the things that they are representing. And then later, Heinrich Hertz, who Helmholtz worked with in the 1880s, and even earlier, I think, but I think definitely the 1880s, had this theory called the picture theory or the image theory, where he argued that a theory of mechanics provides an implicit representation, picture, image of a theory, and that then influences directly Hilbert's account of theories. which is a very long story, a very long history that I can't, but you're absolutely right to pick up on this, because it turns out that Helmholtz earlier on has even a kind of direct account of how things are represented through theories. But then later he accepts something closer to the Hertzian picture, which puts him closer to Hilbert. So later on in his career, he takes on something that's closer to and I think that Hilbert then becomes very, very much a precursor of model theory, to get to the central point of your question. And so I think that there is actually a historical argument for putting Helmholtz in this context. So that's the historical point. In terms of the substantive point that you were talking about, I think you have to be a little bit, you meaning me, have to be a little bit careful, because you don't want to attribute something to someone after the fact. So I think this is the reason why I pointed out the historical point first, is because I think there's a lot of development that has to happen after what Helmholtz has to say in the 1850s and 60s before you get to Hertz and then to Hilbert. And so I think that whatever is present in Helmholtz's view is present kind of in an inchoate and undeveloped form. So I don't think that Helmholtz would have thought of what he was doing as like what we're talking about in model theory, for instance. But I think that there is an argument to be made that his argument about friction in particular does have exactly the similarities that you're talking about. And I think that the historical development of what happens after Helmholtz and when we get to Hertz and Hilbert and the others gives us an indication that at least he would have been sympathetic to that reading of what he was doing. Because I think that he definitely did. He was sympathetic to Hertz's approach. I think he would have been sympathetic to Hilbert's approach. And so I think that but he didn't. He died before Hilbert came up with a lot of his results. But I think that certainly the commonalities that you mentioned are there. And as I say, I think that there's a historical argument to be made that Helmholtz was sympathetic to that kind of approach. And it's very interesting because the idea that a theory is as strong as what it can model does, in some sense, appear in that 1858 paper, because he does give a comparison between his theory and Euler's and Lagrange's theories. And you're right to pick up on exactly that point, that he argues, and I was smiling when you said this, because I think I'm not sure that that Helmholtz can prove this entirely, but he makes the claim that he can prove everything that Euler and Lagrange can prove. I wouldn't want to go up against a real mathematician in defending that that's necessarily the case, right? But he does argue so. And so in a sense, that's you're right to pick up on that, because that is exactly the kind of argument that one wants to make at some point, that what you can say in a theory to some extent delimits what you're able to prove. And so Helmholtz says, well, he's able to give a kind of structure that deals with friction, and that allows him to prove more than Lagrange's and Euler's theories, not because he's able to give a new proof, but because he's able to demonstrate this new structure. He's able to talk about friction in a more in a more specific way, or in a way that actually demonstrates it as a system. And that's what allows him to actually give these new proofs. And so I think you're absolutely right to draw that connection, for sure.
Yeah, thank you very much. The thing is, from a historical point of view, it's interesting, maybe as you know, that it goes from Heinrich Hertz to Tractatus by Wittgenstein. And the thing is that there is this kind of atomistic problem with Wittgenstein. And that's why I'm so interested in your point from a systematic point of view. What's the logical form, so to speak, of a basic construction? And if you say it's a variable, usually we mean an atomic sign. It comes to a structure, and I think it was the main problem in Wittgenstein, and go next step, to find, so to speak, a new logical form, which is not atomic. It was the main struggle of Wittgenstein was that he give up, so to speak, the atomistic program in the Tractatus in the context of Hertz, because he was in the context of Hertz that time. But when you try to start, so to speak, with complex structure, there is this nice paper by Wittgenstein from 1921 in some remarks on logical form. And he tried a lot of forms, put everything, numbers into names and so on. And then you give up the whole story because they thought that it's not possible to get a, so to speak, a real logic if you have non-atomic expressions at the bottom. And if you say that friction is the structure and it's, so to speak, the basic thing for thinking about fluids and so on, it's a very interesting point. So it's only, so to speak, an inspiration. It's not saying that Helmholtz is doing something, but I think it's interesting to find it in Helmholtz, maybe, and to think about this.
Absolutely. Yes, that's fascinating. I didn't know that. Yep.
So thank you. Okay, we have one more question, Professor Anna. Yes.
Well, thank you very much for your very interesting talk. You made a very clear distinction between explanatory and systematic unification. And then you claimed that, nevertheless, explanatory unification was necessary for systematic unification. And then there was this discussion about the historical development of Helmholtz thought from initial, let's say, Kantian point of view, or to a later position which was not so Kantian, or not strictly Kantian. And I was thinking that perhaps, the relationship between explanatory and systematic unification perhaps is not only a one-way relation. If we put this in Kantian words, explanatory relations or explanatory unification is necessary for systematic unification, because otherwise systematic unification would be blind.
Mm-hmm.
Systematic unification is necessary for explanatory unification, because otherwise explanatory unification would be empty. So I wonder if this shift in Helmholtz's position really implies a completely break of the Kantian scheme, a breakdown of the Kantian scheme, or it is rather a question of emphasis on one aspect, on one moment, and the other moment of the whole problem. Put it with other words, you made this description of the relationships of the relationship between explanatory and systematic unification in terms of top-down and bottom-up descriptions. But if we use Cassider's terminology, the system of physics is not a pyramid. Right. So it's more like this Parmenides sphere of well-rounded sphere. So, perhaps we are talking about two different moments of a unity, and the shift in Helmholtz thought, or the shift in Helmholtz interpretation of the problem of the system of physics, is just a shift in the emphasis in one aspect or the other, and not a completely breakdown of the whole scheme. It's just,
Yes.
I don't know.
Yeah. No, I think that's a very perspicuous way to put it. I think that so I think that's a very helpful distinction. That early on, Helmholtz was making one Kantian point that he later did disavow to some extent, that certain causal laws were transcendental conditions for the possibility of science or experience, right? But that later on, as you say, he still made an argument that laws or explanatory unification are necessary to systematic unification. And I have insisted, and I think that you're right to say that that is, you could read that as also a Kantian point, you know, and certainly the neo-Kantians read that as a Kantian argument, and the neo-Kantians broadened what could count as a Kantian argument, certainly. But I think, as you say, you can find that argument directly in Kant, that in order to interpret our intuitions, we have to be able to bring concepts or principles to bear, right? That's certainly that is, in some sense, the Kantian argument. And so I think that one could make that argument that this is really a shift from a kind of more restricted notion of the transcendental to a broader notion that some kind of law is necessary to interpret experimental results, for instance. And I think your question puts that very richly, and mentioning Cassire's point is very apposite. But I think that that's exactly, I think that makes perfect sense as an interpretation of what Helmholtz was doing. I would say that, you know, there are other ways. He two things. One is that is a very good way also of distinguishing between what Helmholtz is doing and what Mach is doing later, slightly later. It's a very useful way of distinguishing between the two. But secondly, I think that there are other possible sources other than Kant and the neo-Kantians for what Helmholtz was doing later in his career. And so that would be the one complication, would be he does, I think, have a position like what you're talking about, where the some notion of law or conceptual analysis is necessary to interpret experiment. But I think that there are people other than Kant who could be responsible for that. Heinrich Hertz is one of them. And there's this tradition moving more towards the sort of model theory tradition that becomes much more in the ascendant toward the end of the 19th century. But I think that certainly there are always vestiges of the Kantian tradition left in what Helmholtz is doing, for sure. And I think it's worth pointing that out. Yes. Thank you.
So, yeah. Okay. So I think that's it for today. Yeah. I would like to thank Professor Lydia Patton for accepting our invitation and for being here and presenting her interesting presentation. Yeah. I would like to thank Lucas Baccarat also for discussing it with her. Thank you, Professor Thomas Übel and Professor Peter Simons, and also Professor Mark Textor, which couldn't stay with us until the end, for joining us here. And I would also like to thank those watching on YouTube and those in the audience. And as I said yesterday, throughout the event, we're just broadcasting the morning sessions and not the afternoon and evening sessions. Right now, in the afternoon today, we'll have a conference presented by Professor Erna Pringe and Professor Ingolf Max. So if you are in São Paulo, I would invite you to come here to PUC São Paulo. And that's it for today. We see each other tomorrow at 9 a.m. UTC -3. Thank you, guys.